Hi, and welcome to the next lecture unit in Chapter 3, which is on simple multi-class to binary reduction techniques, specifically on the one versus rest and on the one versus one scheme. So in this lecture unit here, I want to explain how I can turn any binary classifier simply through these reduction schemes into a multi-class system, into a multi-class classifier by solving a sequence of binary problems defined from the original multi-class problem. So these reduction schemes are nowadays not that important anymore because we have these direct multi-class losses also available to us, and usually they allow us to train multi-class classifiers in a more efficient and direct manner. On the other hand, I think these reduction schemes which occur in or are available to us for many different scenarios in machine learning are quite important. They're quite convenient, especially from a software engineering perspective, where you can now build complex systems from simple ones, often in a model agnostic fashion. And so I want to study these reduction principles here now in a very, very simple scenario, because I think this is quite instructive still. And at least in some software, they are still put to use, especially for support vector machines. So assume we only have a binary classifier in front of us. We don't have a multi-class version of that classifier available to us. And this binary classifier now either outputs direct hard class labels, scores F or probabilities pi, and we want to turn this binary classifier into a multi-class classifier by solving a sequence of binary classification problems. And I will do this through a general principle of defining this reduction scheme from multi-class to multiple binary problems through the codebook approach or the codebook notation. And this codebook notation might seem like a little bit like overkill for these two simple methods like one versus rest and one versus one, but it will prove useful in the next lecture unit where I want to generalize this principle. And anyway, it allows in a very compact and precise form to mathematically define how these binary problems are formed. So I'm using it here too in this lecture unit. So, like I said, what I want to obtain or define is this reduction and encoding scheme for my two-class binary subproblems defined on my original multi-class problem. So usually I read these codebooks in a column-by-column basis, and each column defines a binary subproblem. And all of these entries here in that column now define to me how I should encode my original classes or the observations belonging to that original class in terms of a new encoded Y label. So, for example, here in this first column, I would say that all observations from the first class, from the first original class, now form my new positive class. All observations from the original second class form my new negative class, and all observations from my third original class are actually omitted in this binary subproblem. And in the second binary subproblem, I would merge the classes 2 and 3 to form my new positive class, and my negative class is simply consists simply of all of observations from class 1. And here for the third column, all observations from 1 and 3 are merged to form the new negative class, and the observations from class 2 become my new positive class. So I have now for this specific codebook here 3 binary subproblems, and I would train 3 binary classifiers with my given algorithm on these subproblems. And yes, I haven't really defined now how I can actually predict from such a set of models, or you could also say from such an ensemble, but I have defined at least how the training process can be implemented. And let's now study our first example, which would be the one versus rest principle. So that's super simple to define. So for a G-class multi-class problem, we now create G binary subproblems, where in each binary subproblem, the kth original class forms the positive class, and all other classes form the negative class. So what I'm basically now doing is I'm training G classifiers where I'm always trying to discriminate one class from all of the other classes. So here's the codebook. So here we have this class as the positive class and the rest, second class as the positive class and then the rest, and here the third class as the positive class and here the rest. And here you have visualized this, how these binary classifiers might be formed if we, for example, would use a linear classifier, maybe something like a logistic regression or a linear support vector machine. But of course, we could also use nonlinear systems here. So this doesn't. This is what I mean when I say model agnostic. So this only refers to this coding scheme here for the binary subproblems. I don't make any assumptions on how my F should look like, what algorithm I'm running for this, except for that I'm usually running the same algorithm with the same hyperparameters. How do I now form predictions? Well, usually I would assume that my classifier in the one versus rest scheme gives me access to confidence scores, and then I just pick. So for a new observation X, I would predict all my G binary classifiers on that X, and I would gather all predicted scores and then simply predict the index of the binary classifier with the highest score as my predicted class. So I would use that guy to predict X, I would use that guy to predict X, and I would use that guy to predict X, and which of these guys actually forms the highest score, maybe this guy here, then defines which class is actually predicted. So in this case, the second one. Because in that case, confidence for the second class in these binary comparisons would be the highest. Obtaining calibrated posterior multiclass probabilities is not completely trivial from something like that. Also, even if you would assume that your binary classifiers also output posterior probabilities, these are usually not calibrated well enough. And also, just for a simple problem, consider the fact that all of these posterior probabilities, these G, they don't even sum up to 1, right? When you're solving these G binary problems. But one way to obtain calibrated posterior probabilities is to assume that you are given these G scores here, and then you kind of fit a second stage softmax logistic regression model on these output scores, which transform these output scores into your labeled class or probabilities for such a labeled class. So you actually would treat these scores here from your G binary classifiers as kind of second stage input features, then use your original class label as the label of such an observation, and then train, for example, a softmax regression on that, so that these score vectors here are transformed into well-calibrated posterior probabilities. The second method that's even more popular is this 1 versus 1 coding scheme, which works like this. So in this case now, again, the name is quite intuitive. We create binary pair subproblems where each individual class is trained against each other individual class. So in this case, we create G over 2 or G times G minus 1 divided by 2 binary subproblems. So that's the number of all unordered pairs, where each subproblem consists of observations of exactly 2 classes. So for each subproblem, we pick a pair, for example, 1 and 2, and then this 1 here becomes the positive class, and this 2 becomes the negative class. And of course, should only do this in one way, right? Because now encoding 2 as the positive class and 1 as the negative class is by symmetry exactly the same classification problem, so we don't need that. We only have to consider unordered pairs of classes. And here we do this, for example, for the first and the third class. And then here we have the pair of the second and the third class. And visually, this looks like this. So, for example, we train a classifier on blue versus green. We train a classifier on red versus green and on blue versus red. And in total, for example, so this gives you G over 2 classes in general. So, for example, if you have 5 original classes, this is 5 times 4 divided by 2, so 10 new binary classification problems, or for G equals 10, you would have 10 times 9 divided by 2, so 45 binary classification problems that you would have to solve. How do you do label prediction in such a case? So usually you would assume that your binary classifiers can all output hard labels. Well, they can always do that, right? Even if they predict scores or probabilities, you can just turn these by thresholding into hard labels. And then you simply perform majority voting. So you predict a new observation X with all binary classifiers, and you count how often class 1, class 2, class 3, class 4, and so on is predicted in these binary comparisons. And then at the end, you simply select the class that occurred most often in these binary predictions. There's also a more complicated technique also to transform the scores of these binary classifiers into probabilities, which I will not cover here. So this is called pairwise coupling. And I've at least referenced the paper where this is explained. Let's compare 1 versus 1 and 1 versus rest a little bit, at least in terms of computation time. So first of all, note that each binary problem in the 1 versus 1 coding scheme has now less than n observations. So, or let's maybe count numbers of binary classifiers first. I guess we did that before. So, I mean, obviously, in this coding scheme here, you're only creating G binary classifiers and G binary subproblems for 1 versus rest, and for 1 versus 1, you are approximately creating a G squared divided by 2 binary subproblems. So that appears to be much, much worse. So it's not as bad as that sounds. So 1 versus 1 is more expensive than 1 versus rest. But it's a little bit less worse than it sounds at first glance. The reason for that is in this coding scheme here for 1 versus rest, you are for each binary subproblem using all of the observations. So you just recode their class labels. So here using n observations here and here. For 1 versus 1, you're actually using much less. You're only considering the observations from 2 classes. And if you have a lot of classes and you would assume that they are roughly of equal size, and you have many classes, for example, you have G classes, then in each of these, in this positive and in this negative class, only n divided by G observations would fall. So that's much less than n. We can now also experimentally investigate this a little bit. So I ran a very, very simple toy example here to kind of demonstrate this scaling behavior. So I trained a support vector machine on an artificial data set with 1,000 observations. And what you can see here, so I increased the number of classes more and more and more here on the x-axis. And then in this green plot, you can see how the training time of one versus rest scales with the number of classes, and you should see that this scales in a linear fashion with the number G of the classes. And what you can see here as dotted lines is simply the number of classes computed as G itself, and as this G times G minus 1 divided by 2 formula. And this red line here is how the training time for the 1 versus 1 classifier now scales. And you can see that this is much slower than 1 versus rest, but it doesn't scale proportionally here to this quadratic curve. So it's a bit less than this. And the reason, especially here for the support vector machine, is so you have to consider now a bit what happens with the training time of each of these binary classifiers. So your number of classes, your number of observations goes down from n to n divided by g, or 2 times n divided by g, I guess I should say. So this goes down with the number of classes in a linear fashion. So now you have to consider how computationally expensive each of your binary classifiers is in terms of n. And many of our binary classifiers that we are studying is, for example, scaled quadratically in the number of observations. So the support vector machine does exactly that. It's actually a little bit more expensive. So usually training algorithms scale with n to the 2.2 or n to the 2.3 for the SVM training algorithm, which means if you are halving your training data points, you become 4 times as faster. And this is the reason why, although you have to train this quadratic number of binary subproblems, because all of the individual binary subproblems contain much less observations, training time doesn't scale that badly. There's usually another reason why 1 versus 1 is somewhat preferred from a learning or modeling perspective. So again, consider this graphical depiction here. So what I have to do in 1 versus rest is I have now to find. So assume, for example, that you're only using simple binary classifiers, for example, linear ones, or not super complex nonlinear ones at least. I now have to find a simple decision boundary that separates this one class here from all of the others. And usually this is much harder with a simple decision boundary than simply separating one class from one other class.